Today we are going to learn about mastering stratified cross validation techniques. You'll gain the skills to implement stratified cross validation, a technique crucial for handling imbalanced datasets and achieving more reliable model evaluation.
Welcome to our video on mastering stratified cross validation techniques. Stratified cross validation is a modification of cross validation, which ensures that each fold of your dataset has the same proportion of classes as the entire dataset. This is particularly important in machine learning when dealing with imbalanced datasets, where one class might significantly outnumber others. Unlike basic cross validation, which might not accurately represent the distribution of classes, stratified cross validation preserves this balance, providing a more reliable insight into how your model performs across different subsets of data. By the end of this video, you'll understand why stratified cross validation is crucial and how it can improve the evaluation of your machine learning models. Class imbalance occurs when certain classes in your dataset are underrepresented compared to others. This can lead to models that are biased towards predicting the majority class, resulting in poor performance on the minority class. For instance, in fraud detection datasets, legitimate transactions far outnumber fraudulent ones. This imbalance poses significant challenges, as a model may achieve high accuracy simply by predicting the majority class. Without addressing this issue, the model's performance metrics can be misleading. Effective validation techniques, like stratified cross validation, are crucial to ensure that the model's evaluation metrics accurately reflect its ability to generalize across all classes, not just the majority.
Basic cross validation involves dividing the dataset into K subsets or folds, training the model on K1 folds, and testing it on the remaining fold. This process is repeated K times, with each fold serving as the test set once. However, this method doesn't guarantee that each fold will reflect the class distribution of the entire dataset, which can be problematic with imbalanced data. Stratified cross validation addresses this by ensuring each fold has the same class proportions as the full dataset, making it a better choice for imbalanced datasets. This technique ensures more reliable and generalizable model evaluation results, highlighting its importance in real-world applications.
Implementing stratified cross validation in Python is straightforward, thanks to libraries like scikit-learn. First, ensure you have the necessary libraries installed, namely scikit-learn and pandas for data manipulation. Begin by importing stratified fold from sklearn.model_selection. Load your dataset using pandas, ensuring it's properly formatted. Next, define the stratified fold object, specifying the number of splits. This object will manage the division of your dataset into stratified folds. Use the split method to generate indices for each fold, allowing you to train and test your model accordingly. Throughout this process, monitor your model's performance metrics to ensure it can generalize well across different class distributions. To truly appreciate stratified cross validation, it's beneficial to compare it against basic cross validation, especially in scenarios involving imbalanced datasets. Basic cross validation may not accurately represent the dataset's class distribution in each fold, which can skew performance metrics, leading to biased evaluation. For instance, in a dataset where 90% of instances belong to one class, basic cross validation might create test sets heavily skewed towards that class. In contrast, stratified cross validation ensures each fold mirrors the overall class distribution, providing a more balanced and fair assessment of model performance. Through various case studies, it's evident that stratified cross validation consistently offers more reliable evaluation metrics and insights. While stratified cross validation is powerful, it's not without its pitfalls. One major concern is data leakage, which occurs when information from the test set inadvertently influences the training process. Always ensure that data preprocessing steps, like scaling or encoding, are applied separately to training and test data within each fold. Additionally, it's crucial to interpret results correctly. The stratification process might not eliminate model overfitting if the model complexity is high. Consistency across folds is also essential. Variations in preprocessing or feature selection can lead to misleading performance metrics. Being aware of these pitfalls will help you leverage stratified cross validation effectively and avoid common mistakes. Interpreting results from stratified cross validation requires a nuanced understanding of performance metrics. Look beyond accuracy, evaluate precision, recall, and F1 score, especially in imbalanced datasets. Stratified results often provide a more consistent view of how your model generalizes across varying distributions. Analyze variance across folds. High variance might indicate instability or overfitting. Accurate reporting of performance metrics, with confidence intervals, can offer deeper insights into your model's reliability. Understanding stratified results helps in assessing model generalizability, ensuring it performs well not just on the training data, but on unseen, real-world data as well.
Stratified cross validation is widely used across various industries to enhance model reliability and performance, particularly in fields dealing with imbalanced data. For instance, in the healthcare industry, models predicting disease presence often face imbalanced datasets, where the majority of patients do not have the condition. By applying stratified cross validation, healthcare practitioners ensure more reliable predictions, directly impacting patient care and treatment plans. Another example is in finance, where fraud detection models benefit from stratified techniques, providing more balanced insights into fraudulent versus legitimate transactions. These applications underscore the value of stratified cross validation in making informed business decisions and improving overall model robustness. Deploying models evaluated using stratified cross validation involves ensuring robustness and adaptability. Monitor model performance over time, particularly as new data becomes available. Stratified validation should be an ongoing process, continuously assessing model performance and adjusting as necessary. Integrate stratified validation into your workflows, allowing for dynamic updates and retraining of models when significant shifts in data distribution occur. Employing these best practices ensures that your deployed models remain reliable, providing consistent performance and valuable insights, even as data and scenarios evolve. By incorporating stratified cross-validation into deployment strategies, you can maintain high standards of model evaluation and effectiveness.
In conclusion, mastering stratified cross-validation is a valuable skill for anyone working with machine learning models, particularly those dealing with imbalanced datasets. This technique not only ensures more reliable model evaluation but also enhances the generalizability of your models. We've explored its implementation, compared it with basic cross-validation, and discussed best practices for deployment. Remember, the goal is to consistently apply these techniques to achieve robust, accurate, and insightful models. We encourage you to integrate stratified cross-validation into your machine learning workflows, ensuring your models are well equipped to handle diverse and challenging datasets.